Good morning, everybody, and welcome back to the second day of the third annual Chicago Quantum Summit. And for those of you who just joined, I'm David Aushalom, the Liu Family Professor in Molecular Engineering and Physics here at the University of Chicago, a senior scientist at Argonne National Lab and director of the Chicago Quantum Exchange. We have a very full day planned today, and we'll begin in just a moment. But I'd like to start by saying I'm really pleased to announce that Governor J.B. Pritzker will join us this afternoon at 1 p.m. Central Time to discuss the impact of quantum science and engineering here in the state of Illinois. So please stay tuned for that. So to kick things off this morning, we're fortunate to have Dale Van Harlingen, the Donald Bigger Willett Professor of Physics and Engineering at the University of Illinois at Urbana-Champaign, who's going to moderate today's sessions. So to get going, we'll begin today's program by hearing from Sethuraman Panchanathan, the director of the U.S. National Science Foundation. Dr. Panchanathan is a computer scientist and engineer with more than 3 decades of experience in both higher education and in government, where he's designed and built knowledge enterprises that advance research innovation, strategic partnerships, entrepreneurship, global development, and economic growth. He's done a lot for all of us. We're delighted that Dr. Panchanathan will share with us how he and other members of the NSF are thinking about quantum information science, and we'll talk about the agency's recent and clearly very significant investments in the field through the recently awarded Quantum Leap Challenge Institutes and other programs. Thank you very much for joining us today.
Thank you very much, Professor Aushalom. First of all, let me tell you, I'm so excited to be part of this important conference because this is focused on an area, I think, which is very important for our nation. So thank you so much for organizing this meeting. And I'm so impressed with the attendees that are able to join today because of the virtual format, which would be a lot more than what it would be if we were all physically together. That is one of the advantages, if you call it, in these sort of complex times. And to Professor Aushalom, being a member of our advisory committee for the mathematical physical sciences, your service, sir, is exceedingly important to how NSF is moving forward. And I'm so grateful for your service and your leadership in the area of quantum. So what I thought I will do is today share with you the overall context of what we are doing at NSF and specifically focus on strengthening quantum research and what I would call it at speed and scale. Because we all know that quantum research is something that has been there for several decades now. But now what we're doing is we're putting an extra emphasis to make sure that we're able to strengthen that research at speed and scale. So let me place the NSF mission in context because some of you may be familiar with this, but I'm going to quickly sort of place the NSF mission in context. You're all probably aware that the key components of NSF mission are promoting the progress of science, advancing national health and prosperity, as well as securing the national defense. This three-pronged approach of trying to make sure that NSF's mission, which has been vibrant for the last 7 decades of NSF's existence, and that this is time-tested, that it is going to advance us into the future, not only in this decade, but decades to come. So I'm very excited that this mission clearly aligns with everything that we are going to be talking about in respect to quantum, which is the focus of the presentation today. So NSF's ability to support research over the long term has brought us to a moment of tremendous potential for quantum science and technology. We all know that. We have answered many fundamental questions about what happens at the quantum scale. And as a result, we have had many new questions to answer and areas to explore, which is very exciting as a prospect going forward. I'm confident that we are going to be making bigger breakthroughs and greater breakthroughs. And they're also going to happen faster. And even more important, we are going to translate some of them into exciting new applications. To do this, NSF is focused on expanding the reach of quantum throughout the whole country. We are building partnerships that are going to enhance our ability to make significant breakthroughs. We are already building the foundation for the future of quantum technology. When you look at this context and you start to then contextualize this mission into the vision that I have started to outline for NSF as we move forward, it is made up of 3 pillars. Advancing the frontiers of research into the future, no surprise there. Ensuring accessibility and inclusivity, this is something that I deeply care about. And I know that all of you do care about this too, that as we're advancing ideas like quantum, AI, and others, that we need to ensure that all parts of this nation, the socioeconomic, demographic, and the geographical diversity of the nation, are part of this exciting prospect of making a huge impact in science, technology, and engineering for our nation, and therefore a prosperous society and economy for our nation. So this is an exceedingly important imperative, and I'm going to come and talk about this a little bit more when we talk about people. I know that you're all thinking about this too as part of this meeting. And the third pillar is securing global leadership. And one of the major areas of global leadership, and when I talk about global leadership, it is in a form of a shared leadership with those like-minded partners who we deal with, who share our values, who share our aspirations, who share, more importantly, our desire for scientific progress made through openness, transparency, reciprocity, at the same time having tremendous respect for research integrity. All of this is what makes us share this global leadership platform with leading countries across the globe. Now, when you look at all of these pillars, you have this fundamental core of partnerships, and we're going to talk about this more in the context of quantum, and that we do all of this with an innovative mindset, an innovative spirit that permeates everything that we do at the agency and what agency then unleashes across this great nation. So I'm just going to dive into the quantum-related activities, and when you're talking about advancing frontiers, advancing the frontiers of science at NSF, there are many different things that we look at, which is curiosity-driven research. As we know, curiosity-driven research is the core of NSF mission and a driver of economic growth and societal prosperity. All of the potential benefits of science, technology, and engineering we see today are driven by the unbelievable power of exploratory, discovery, and curiosity-driven research. So strengthening the benefits and progress of curiosity-driven research at speed and at scale will require renewed focus on partnerships, people, and translation. And I'm going to go through them very, very quickly in the short presentation that I have the opportunity to be with all of you and share with all of you. NSF has been funding, as you all know, foundational quantum research across multiple fields of research for decades. Chemistry, material science, and mathematics divisions within the Math and Physical Sciences Directorate have been leading the charge. Clearly, more recently, computing communication foundations within Computer Information and Sciences and Engineering Directorate, electrical computer and communications and cyber systems within the Engineering Directorate. These accomplishments are the results of nearly 4 decades of sustained investment in the spectrum of scientific fields that underpin the potential for quantum. For example, in 1979, NSF made a grant to Kip Thorne for a new quantum measurement technique that is now part of the advanced LIGO project. NSF began funding quantum information science in the early 80s. We have funded 31 Nobel Prize winners for quantum breakthroughs. In 2017, NSF designated the quantum leap as one of its 10 big ideas. I was part of the National Science Board as we were configuring these 10 big ideas, and I was so excited to see the quantum leap as a significant move forward on that. Over 40 years, more than 2,000 awards have been made to more than 12,000 investigators in the area of quantum. So we know that multidisciplinary research is critical to the progress of the whole range of quantum research fields. That will be a key factor in our approach to NSF strategy moving forward. Quantum Leap Challenge Institutes are large research centers, advanced areas of quantum information science and engineering. Let me draw this for a moment. When I look at the bubbles around, I'm not going to be able to throw all of them as examples of what we would talk about NSF's exploration into the future. But if you look at the research centers, even the engineering research centers that were announced in the last recent cycle of competition 2 months ago, one of them was on quantum networks at the University of Arizona. And then we have the National Quantum Platform-like thinking, some of which I'm going to share today, which is based on the unbelievable work that has been put in as foundation over the years of investments in quantum that we talked about. And that quantum will be, as in AI, across the nation, potentially in every state of the state nation. So when you look at the frontiers of quantum information science and engineering, the Challenge Institutes support large-scale projects. They focus on bold research agenda aimed at making big breakthroughs on important questions. They are speeding research by focusing on major advances that can be made in 5-year periods. They are part of training the workforce of the future that will rely on strong cross-disciplinary skill sets necessary for quantum information science and engineering. You all know this. I'm probably preaching to the choir here, but I just want to anchor this in the kinds of things that NSF is doing and will be doing so that you are all privy to that information. When we talk about the three quantum challenge institutes, the first one was the NSF Quantum Leap Challenge Institute for enhanced sensing and distribution using correlated quantum states. This institute, led by the University of Colorado, will design, build, and employ quantum sensing technology for a wide variety of applications in precision measurement. Quantum sensors that can measure everything from radiation levels to the effects of gravity will be more sensitive and accurate than classical sensors, enabling a tremendous range of new technology and applications. The second institute, the NSF Quantum Leap Challenge Institute for Hybrid Quantum Architectures and Networks. This is something that you as an audience will be very familiar with because it's right there in Illinois. They're developing more robust quantum processors, which is a significant challenge in quantum information and science and engineering, is led by this institute at the University of Illinois Urbana-Champaign, which will build interconnected networks of small-scale quantum processors and test their functionality for practical applications. This is important work for building up the capacity for quantum systems and network that can reach farther and deeper than anything else. The third institute, NSF Quantum Leap Challenge Institute for Present and Future Quantum Computing. Today's quantum computing prototypes are just the beginning. There is a great deal of progress to be made building on these first designs. There are still so many questions on how to increase the scale of these prototypes, as well as how to reduce errors and speed performance. Therefore, this institute, led by the University of California at Berkeley, plans to learn from these to design advanced, large-scale quantum computers, develop efficient algorithms for current and future quantum computing platforms, and ultimately demonstrate that quantum computers outperform even the best conceivable classical computers. These are the three challenge institutes in place now. They're just the beginning, we all know that, with the second phase of competition for the next set of institutes underway. There are other initiatives, these and other initiatives as well, that are important for putting the possibilities of quantum technology closer to our reach. For example, the Quantum Foundry at University of California, Santa Barbara. The Quantum Foundry is developing the materials and interfaces that are integral to how quantum systems will power new technology. Decades of advances in traditional computing and technology were powered by innovations in microelectronics and new materials that allowed for greater efficiency and performance. Now, that work to build the materials and components that will enable quantum systems is the beginning at the Quantum Foundry. As I said, this is all the things that curiosity-driven research over the last 4 decades and what we're embarking on right now through these conceptualizations is making possible. But we need to do more as we are expanding these activities at NSF. This is just, as I said, the quantum across the nation through the various initiatives that we have put together as a map of various activities that we have funded at NSF. Now, if you start to look at how might we accelerate it, I talked about this at speed and at scale that we want to engage in, so to further accelerate progress. Now, you can think of them as megatons of rocket fuel being added to already the fantastic work that is being implemented across the nation and the decades of work that I talked about that has happened. So now we are talking about how we might do more. So partnerships are clearly a methodology for strengthening and scaling and speeding our advancements. You can think of it like a turbocharging the engine of the research enterprise. So one of the areas that NSF will be focusing is how to focus on partnerships and taking them to a new level. So NSF is fostering partnerships at every level of our mission. Every day we are thinking about newer and newer forms of partnerships within the agency, across agencies, with industry, with states, with cities, with K-12, with community colleges, with university systems, as well as with international partners. So multidisciplinary and convergent research within science and engineering disciplines are an exceedingly important imperative to make rapid progress. Interagency partnership investments, for example, with the Department of Energy and other federal agencies is already happening in the area of quantum. So NSF is a proud partner with the White House Office of Science Technology Policy on the National Quantum Initiative. This is a multi-agency approach within the federal government to advance quantum technology and quantum computing. It also includes the National Institute of Standards and Technology, NIST, Department of Energy, and others. And we are working to grow our partnership with industry. For example, working with quantum computing research programs at Amazon, IBM, Microsoft, and others, NSF is working to make cloud-based quantum computing platforms available to researchers. Going forward, NSF's goal is to expand the reach of where quantum research happens. Currently, the majority of quantum research tends to cluster on the East Coast, West Coast, and the Great Lakes region. But there is tremendous capacity for quantum research throughout the nation. We want to extend the reach of quantum research to more geographic areas of the nation, as well as expanding the quantum research happening at different types of institutions, including minority serving institutions, MSIs, Hispanic service institutions, HSIs, historically Black colleges and universities, HBCUs, and others. At the University of Nebraska-Lincoln, the Quantum Sensing and Defect Discovery and Spectroscopy Lab in the Mechanical and Materials Engineering Department are studying a wide range of quantum phenomena, including condensed matter physics, quantum optics, and nanoscale metrology. Their work is focused on quantum sensing, novel solid-state materials, and methods to achieve scalable quantum networks. At Georgia Tech, Colin Parker was awarded the NSF Career Award this past summer for his work on quantum simulation, allowing researchers to model materials and conditions that are difficult to accomplish in a laboratory or that would require a supercomputer to simulate. In addition to training graduate students, the award will support high school students and teachers from the Atlanta area to work in the lab over the summer on mechanical and electronic automation tools to increase lab productivity. These are partnerships at every level that we can continue to grow. How can we broaden the disciplinary focus of participants in quantum research? How can we continue to expand the government and industry partnerships we have? Quantum information science and quantum computing can support a wide range of government operations beyond the energy and defense departments. The same is true for a wide range of sectors in our economy. How can we bring more end-user communities into the development of quantum technology and applications? The biological sciences are an area where end users could greatly benefit from advances in quantum applications. There are a wide range of processes and applications in biology that are quantum phenomena: chemical reactions, charge transport, magnetoreception, photon absorption and vision, photosynthesis, and others. In 2018, NSF funded a workshop on quantum biology and quantum processes in biology. By integrating quantum information science, biologists can boost progress and lead to new insights. The second turbocharging engine that I talk about is people. We need an agile and adaptable workforce that can upskill, reskill, and succeed through creative and innovative mindsets. Quantum science and technology have enormous potential to boost our economy. Quantum computing and quantum applications have the power to transform how entire industrial sectors operate. That's indeed very exciting. But to realize all of the potential gains to our economy, we must invest in the education and training that the workforce requires. Investing in STEM education is a core part of the NSF's mission. In order to meet all the promises that quantum science can bring to the workforce, NSF is expanding our investments in quantum education and training at every level. For example, the National Q12 Education Partnership. I was there at their launch the other day. Partnership, where NSF and OST co-sponsored workshop connecting the communities of university and industry researchers, secondary school and college educators. The National Q12 Education Partnership will enable best approaches, activities, and evidence-based strategies to increase diversity in QIS education. Next, NSF Quantum Computing and Information Science Faculty Fellows Program, QCIS-FF. Program to encourage departments and schools in US universities to hire new full-time faculty in either tenure track or tenured roles in quantum computing and or communication. There are 13 awards already made to date in this area. NSF is supporting innovative new approaches to enhance training in quantum science and technology. The Quantum Information Science and Engineering Network, for example, QISC-NET, is one-of-a-kind national training program for graduate students pursuing careers in quantum science and engineering. We know that we can enhance educational outcomes through mentoring and partnerships. There are many programs that focus on connecting students with faculty mentors or industry mentors. This program goes a step farther than pairing students up. Instead, we are forming triplets that include a student, a faculty, and industry coming together. People really, as we know, are the heart of the research community. I said this earlier. It may sound like a slogan, but consider this. NSF is not the biggest federal investor in federal quantum research. The Department of Energy has spent approximately 4 times as much money as NSF has in quantum research. And they are not the only ones. The Department of Defense is making significant investments. Industry is making investments. The thing that sets NSF apart is people. Because we are training students, that's an important distinction. We are supporting undergraduates and graduate students who are starting out as quantum researchers. We are funding postdocs and early career researchers. We are supporting multidisciplinary research and convergence research. So even when DoD or another agency makes big investments in quantum, it is the science and engineering community that is doing that work. All of you. It is researchers and scientists and engineers that were supported by NSF as students or early career as they embarked in their careers. It's investigators who are studying basic questions about quantum science before there were any hints of applications for industry or government programs. NSF has broader access to a much larger group of talent and expertise, and these people will want to do research at the Department of Energy or DARPA or other agencies. So we need to continue to support the growth of the STEM community. We will need every person in the STEM in order to meet the needs of the future workforce. These are what I call missing millions of students and young people who have the drive and the talent to be scientists and engineers, but might not see the path into the STEM community. How do we create new pathways so that talent from every demographic and community can join the STEM community? Let me mention again, NSF's goal for quantum research and the quantum workforce is to expand the opportunities for young people and students to join the STEM community. By bringing quantum research to more states and expanding the geographical reach of quantum science and engineering, we are going to create new pipelines for talent to join the research enterprise. The third megaton of propellant that is going to propel us is going to be, and I'm going to skip this in the interest of time, these are all the programs that are clearly advancing the inspiration of talent everywhere. But then the third important impetus to advancement is translation. As we all know, translation drives advancement. Scientific knowledge leads to actionable progress, which in turn enriches the scientific process. In other words, science and technology are intertwined. NSF advances technological progress because it is already intrinsic to everything that we do. NSF supports translation through numerous programs. You are all aware of that. ICOR, SBIR, STTR, and many more. Translation is how discovery science becomes solution science. Quantum is a great example of the cycle between basic research and the emergence of new technological capabilities. When I was reviewing NSF history of support for quantum research, I mentioned an award to Kip Thorne for quantum measurement technique for LIGO. What else did that research enable in terms of our ability to design quantum sensors? By improving our technological capabilities to smaller and smaller missions, we enabled more breakthroughs and greater insight into the natural world. This is one of NSF's greatest strengths. We are fostering translation throughout the entire range of research that we support. We are looking for innovative new applications inspired by basic research. We are supporting new research techniques that are enabled by advances in technology. And it is an advantage that NSF has that it is rare in other areas of research. Industry is making significant investments in advancing quantum technology, but often industry does not have the resources or business incentives to explore basic research. Basic research does not always have a clear pathway from the laboratory to technological applications. NSF is able to bridge the gap and do both. We are able to foster partnerships and enable collaboration between industry, academia, and government partners. One of the examples of how NSF is fostering translation in quantum science is a quantum idea incubator for transformational advances in quantum systems, QIITAQS program. This program supports interdisciplinary teams exploring, innovating original ideas in quantum science and engineering. These projects cover a broad spectrum of research approaches and have the potential to deliver new breakthroughs, new platforms, and new approaches for accelerated development of quantum technology. In FY 2019, NSF made 19 awards through the Quantum Idea Incubator. These pioneering projects focus on quantum functionality and advancing quantum systems, from experimental demonstrations to proof of concept validations. The Quantum Idea Incubator is fostering breakthroughs in quantum sensing, quantum communications, quantum simulations, and quantum computing systems. At the University of Massachusetts, a transdisciplinary team of researchers are designing and fabricating new quantum systems capable of sustaining quantum states that is resilient to changes in local environment. This is an important work for quantum computing. So I've shared with you a number of things that NSF is inspired and is inspiring through all of the fantastic ideas and talent that all of you bring and all of you nurture across this great nation. In conclusion, this is all to say that NSF has been building a foundation for quantum science and technology. That foundation includes more than 40 years of investments in quantum information science. That is the bedrock of our progress so far. It includes work to build up the capacity for quantum research across disciplines. We are building the quantum workforce. We are fostering transformational collaborative research. We are enabling new leaps forward through convergent quantum centers like the Quantum Leap Challenge Institutes and Quantum Foundry. The support for basic research will continue to be the main focus of NSF. We are going to continue to drive breakthroughs and advances across the spectrum of quantum science. That foundation has led to exciting new horizons for quantum science and technology. We are beginning the next phase, the big phase of expansion of our understanding of quantum science and our capabilities across the whole range of quantum applications. We are going to expand the quantum research enterprise. That means expanding the reach of quantum research into innovative areas of science and engineering, as well as exploring creative new concepts. We are excited at the potential for new endeavors throughout the nation as we expand the geographic reach of the quantum enterprise. We are going to see the next generation of quantum workforce join the research community. We are going to expand opportunities across the nation so that anyone with talent to join the STEM workforce has a pathway into the community. We are going to continue to focus on education and training. The strength of science and engineering community is going to drive the future of the research enterprise, including in quantum science and technology. We are going to achieve tremendous new applications for quantum science because of all your dedication and hard work. We are investing in the cycle between discovery science and solution science. We want that cycle to happen faster, where appropriate. We are going to make leaps forward in our understanding of quantum science. Those leaps forward will enable new possibilities for quantum technology. And then that technology is going to give us the tools to make new breakthroughs that start the cycle all over. All of you who have joined for the Chicago Quantum Summit today are part of the bright future for quantum science and technology. You represent decades of hard work that made it possible for us to reach this point. And you also represent the enormous potential for the future. We are headed into a bright new area for quantum research. You are driving the progress forward. And I'm very excited to see the breakthroughs and advances that you accomplish in the coming years. And you can be rest assured that you have a tremendous supporter in me helping to make that happen. Thank you so much.
Okay, well, thank you, Dr. Panchanathan, for sharing your vision and for your stimulating review of all the ongoing activities at NSF. We have only a minute or two for questions, but I want to slip in maybe a couple here. This is one I was interested in, but a number of people have put these in the chat already. There's a lot of interest in international programs. Somebody just logged on from Nigeria, for example. We're largely focused on the national program, but as you know, quantum information is really an international effort, and many of us have collaborators all over the world. Can you say a little bit about how NSF plans to interact with comparable quantum efforts in other countries?
Absolutely, Dale. Excellent question, by the way. Let me tell you, if this is an indicator for the international, you will indicate you'll understand the emphasis that I'm putting on international collaborations. 2 days ago, I chaired the Chief Science Advisors call across about 30 to 40 nations. And we talked about what are the collaborative areas that we could work on globally. Clearly, COVID-19 pandemic and the immediate needs that we need to look at in terms of pandemic prediction and what the mechanisms of mitigating and addressing the issues forefront in all our thinking. But then we talked about AI, we talked about quantum and others. Clearly, quantum is a significant part of our thinking in the international collaborations, right? And then yesterday, I had 2 conversations. One with Canada. Canada, as you know, is a great investor in quantum. They've got $1 billion of investment. I've talked to Alejandro Adam, the head of NSF in Canada, as well as Mona Niemer, the chief science advisor, as that being a significant vertical of collaboration between Canada and the United States. And Sweden is an amazing investor in quantum. We are talking about how we might work together. I've talked to Dame Audeline at UKRI and Mark Ferguson in Science Foundation Ireland to talk about how we might work together in the area of quantum as an international partnership. So I can assure you that NSF, through its Office of International Science Engineering, is moving forward in terms of leveraging and be leveraged by this global interest in quantum, and that this is a global effort with global expertise to make substantial progress in a rapid amount of time. And therefore, you can be rest assured that NSF is fully committed to the global nature of this collaboration, and we'll do everything to advance that.
Okay, well, thank you very much. And we are out of time, but I want to thank you again, Panch. We are, I think, very grateful for your strong leadership at NSF and your deep appreciation of the importance of quantum information in the future. And we look forward to many interactions with you. So thank you very much.
Thank you so much. Thank you very much. Have a wonderful day and a wonderful conference.
Great, thank you.